Hello, everyone. As Marcel introduced it, yes, I'm Felipe, and thank you very much, Marcel, for inviting me to share his work. My purpose here is yes to share this work and hear your comments, your ideas, and perspectives on what we have been doing. The title of the work we published it is The Impact of an Antarctic Circumpolar Current Meander on Earth's Interaction and Water Subduction. And I will share this as a conversation. It's not a talk, so feel free to interrupt me at any point and bring up your comment. And then this part will be shared in the first 30 minutes. And the second chapter that is in progress will also be shared in the second half of the conversation. This work was supervised by Nathan Beaneff, Helen Phillips, Stephen Toe, and Max Nikrashin. Let's start as first things first. Let's start with a brief introduction. What is the importance of air-sea heat fluxes? Well, I'm aware that the community here knows about it, but just bringing the room to start with. We are aware that air-sea heat fluxes play a key role in regulating Earth's climate as it transports heat from the equator to the poles. It's relevant for accurate predictions of weather and reliable storm alerts. And the discussions by Sarah Gill, Sebastian Sword, Marcelo Places, and many others highlight us that the air-sea heat fluxes observations from the Southern Ocean are scarce, and we need to improve this discussion for a better global climate discussion to evaluate the impact of the return circulation and the oceanic heat uptake. One question that we can ask in particular for the Southern Ocean is, what are the oceanic factors that are affecting air-sea heat fluxes? And the literature show that the eddies do that for sure. In this work by Luciano Pezes, Roland Buzz, and many others in 2021, they observed a warm core eddy at the Brasilia-Malvinas confluence region. They had 6 XBT deployments that they also crossed with meteorological instruments along the region. And they showed that the warm core eddy in the ocean can increase the surface winds as well as the heat fluxes, and it produces a warm and mixed and unstable marine atmospheric boundary layer at that region. It was an interesting work seeing the effects of the ocean and the marine atmospheric boundary layer. In this work by Ivy Franger in 2013, they evaluated about 600,000 oceanic eddies in the Southern Ocean, and they showed that the eddies modulate the cloud cover, water content, precipitation, and wind circulation. Similar to the eddy at the Brazil-Malvinas current, the warm core eddies in the Southern Ocean that accelerate the winds. And here in this work, we also see that they increase the precipitation. And the cold core eddies, they decelerate the winds and increase the precipitation in the opposite effect. Based on the patterns induced by the eddies, I think we have room to think if meanders could cause a similar effect as the crests and troughs of meanders behave like eddies. I mean, crests behaving like anticyclones and troughs behaving as cyclones. We also have the more room to think about these impacts following the work by Annie Foppert and others in 2017 that they highlighted strong eddy heat fluxes at locations of ACC standing meanders that we see in this eddy heat flux inferred from the standard deviation observed by altimeters that they are intensified at the Kerguelen Plateau, Macquarie Ridge region, and Drake Passage. Moreover, the work by Phillips and Rintel in 2000 highlight that meanders along the Antarctic circumpolar current funnel heat towards Antarctica. So we have room to think, what is the impact of standing meanders in Earth's interaction once they hold enhanced eddy heat flux? Is the impact like the eddies because the crests and troughs concentrate warm and cold waters respectively? Moreover, the work by Thompson and Vera Garbato 10 years ago, they suggested that meanders could hold a mechanism to dissipate the energy input introduced by the winds in the past 20 decades, because in the past 20 years, in the past 2 decades, because in the past 20 years, the winds have intensified in the Southern Ocean, but the ACC transport has remained relatively constant. So the author suggested that the decrease of the wind stress in the region upstream of the meander could tilt the isopycnus, leading to an input of potential energy that the increase of the curvature of the meanders could dissipate this energy increase by the winds vertically through the water column. Our goal here, motivated by the increased eddy heat flux at the Macquarie Meander region and the possible subsurface impact of meanders suggested by Thompson and Garbanto, we will explore then what is the impact of the Macquarie Meander in the regional air-sea heat fluxes and water subduction and the subsurface dynamics. To do so, we use the monthly output from the Axis OM2 ocean model, sea ice ocean model, that is a 10th degree model that is forced by the GRA 55 atmospheric reanalysis. Okay, let's see some of the methods we employed. To estimate subduction, in this part of the work, we followed Cushman-Roising, 1987, and Marshall, Downs, and others, that subduction is linked with the lateral injection of fluid from the mixed layer into the ocean interior, stern, the U at the base of the mixed layer multiplied by the mixed layer depth gradient, and the vertical velocities at the same level. We also needed to know the position of the ACC fronts in the model. To do so, we tracked it then by following the isotherms that were related to local transport maximum, as done by Langley and others in 2011. And we also made a contribution to the method by evaluating a meridional density gradient at the positions of local transport maximum. This figure here illustrates one snapshot of the model that we ran the algorithm. We see a local transport maximum around 52 degrees south, and the meridional density gradient profile at this snapshot at this meridional transect shows that there is a maximum at around 300 meters depth. At this location, the 2.9 isotherm stands as a proxy to follow the polar front. We ran this algorithm over a 26-year period covering longitudes around Australia, and it returned two most frequent temperature values that when we compare with observations and model output in the regions, these isotherms are characteristic to follow the polar front and the southern branch of subantarctic front in the model. In this other figure, we see the polar front in black, the southern branch of the subantarctic front in white, and also the sea surface height gradient. There is another way of tracking fronts. And we see that for this snapshot and other, we evaluated the time series and an animation. These isotherms follow quite well. We also see that the standing meander south of Australia is the Macquarie Meander is between 145 east and 155 east for this snapshot and others we evaluated. So we use these longitudinal boundaries as limits to estimate the length of the meander, to build this meander length time series that based on the mean and standard deviation, we build composites of events when the meander was relaxed and when the meander was flexed. On the right, we can see both the individual snapshots in the thin contours and the composite in the thick contours. We see that for the flexed composite, it has higher curvature than the relaxed that will help us taxing the impact of flexing the meander on subsurface dynamics. But first, let's talk about the impact of the Macquarie Meander on thermodynamics. The figure on the left shows the composite when the meander is relaxed, for the air sea temperature normal in top, the surface net heat flux in the middle, and the mixed layer depth in the bottom. On the top, we see that the ocean is warmer than the atmosphere at the crest than it is at the trough of the meander. We see a wave-like pattern in all of these figures. In the middle, we have the surface net heat flux that contains the sensible heat loss, latent heat loss, long wave, short wave, Kelvin by melting of sea ice, and all of these fluxes. And we also plot here the sea surface height contours that are indicating us that at the crest of the meander, the subantarctic front displaces warm water, polar warp. And as the westerly winds are nearly zonal at this region, we have warm water reaching a region of colder atmosphere. And following the second law of thermodynamics, the system always wants to increase its entropy, and it only occurs if it converts energy from the warmer to the colder state. In this case, there will be heat loss by the ocean at the crest, and the opposite occurs at the trough, as it displaces warm water to a region, as it displaces cold water to a region of warmer atmosphere. In this case, there will be heat gain by the ocean at the trough of the meander. This surface net heat flux has a consequence for mixed layer depth because heat loss leads to buoyancy loss or density gain that causes the deepening of the mixed layer depth. And the interesting fact is that we see that at the meander, there is an additional zonal gradient for the mixed layer depth gradient there's both a meridional, but also a zonal at this region. And upstream of the meander, the gradient at mixed layer depth is mainly meridional that contributes for the mold water subduction. But at the region of the meander, we have an additional component that when we evaluate the composite of the relaxed meander for circulation in terms of the wind stress curve relative to the ocean, the vertical velocities at the base of the mixed layer depth in the middle, and also the subduction, we can see that the meander is able to displace the subduction signal from the region at the subantarctic front to a region that is more polar, closer to the polar front, where it has intermediate water-like characteristics. But let's get back to the wind stress first. Again, as the winds are nearly zonal and at the meander, it's where it occurs meridional changes of the meridional velocities being polarward entering the crest and equatorward exiting at the crest. We see that the meander can introduce a curl back to the atmosphere that we don't see upstream of the meander, where both the winds and the fronts are nearly zonal. For the vertical velocities, at the base of the mixed layer, we see that they increase at the region of the meander relative to the region upstream. Moreover, we saw that the interior ocean vertical velocities at the base of the mixed layer are 10 times higher than the vertical Ackermann velocities, indicating impact of ocean dynamics contributing for the vertical displacement of tracers at meander regions. For subduction, we have both this WH and that lateral induction term. And as I gave the spoiler, we see that the meander region displaces the subduction region polarward. That was something we don't see much in the region upstream of the meander. We also wanted to evaluate the long-stream variability of the air sea heat fluxes and subduction. To do so, we needed to know what were the SSH and isopycnal boundaries to make the integral of the air sea heat flux and subduction values. In this figure, we have the SSH contours. The bold phase one for minus 0.9 is the one representative of the polar front. We picked the temperature and salinity values along this SSH contour, and we saw that the 27.9 and 26.9 capture the minimum salinity characteristic of the intermediate water at this location. And we see that they are bounded by the minus 0.7 and minus 1.1 SSH contours. Then we projected the surface net heat flux from the geographic coordinates we had in the previous map to the sea surface height coordinates. And we made integrals for these SSH boundaries related for polar front domain and also, let's say, intermediate water-like waters and other SSH bands related for other frontal boundaries. We see that for the integral of the surface net heat flux along the intermediate/polar front region, there is an increase in about 13 terawatts for the region upstream relative to the region downstream of the meander. And we don't see much increase where the currents are not meandering, suggesting the impact of the meandering of the fronts in the changes of air sea heat fluxes in an integrated area. We did the same for the subduction. By same, I mean the projection of subduction from geographic coordinates onto the SSH place. We see that at the meander, the subduction values cross SSH boundaries from the subantarctic front region towards the polar front/intermediate water-like domain. And the integrated values show an increase in about 2 variables for this white SSH band that is for the subantarctic front region where mold water is concentrated. And for the polar front band in black, we see changes from abduction to subduction values along the, compared in the region upstream to the region downstream of the meander. Now turning to the subsurface impact of flexing the polar front meander. Here we have the vectors of vertical velocities and it colors the horizontal water divergence. For the case when meander was relaxed, the relaxed composite on top and the flexed composite in the bottom. And the map also helps us see the changes in curvature at each of these composites. And what I see is that for both cases, as suggested, and also, as indicated by both Thompson, Verder-Banto, and Myers and others in 2022, there is divergence and upwelling upstream of the crest and convergence and downwelling downstream of the crest of the meander. The contribution that we make here is to show that when you flex the meander, the divergence and upwelling is much higher than when the meander is relaxed. And the same occurs for convergence and downwelling when the meander is flexed. Okay, so just closing this first part of the conversation, as we saw that meanders enhance air-sea heat fluxes, the crest of the meander host surface heat loss and deeper mixed layer depth, and the opposite occurs at a trough as it concentrates heat gain by the ocean. We also saw that meanders extend the subduction signal because of the increased vertical velocities as well as the lateral injection of fluid crossing this undulating mixed layer depth. And we also saw that the meander flexing leads to enhanced vertical velocity, confirming the previous hypothesis that increased meander curvature enhanced to more water divergence and faster vertical velocity. At last, finally, we see that meanders can locally force the atmosphere as the meander signal imprints a signal back to the atmosphere through the wind stress curve relative to the ocean. The black vectors here show the near surface wind, and the blue ones show the sea surface velocity. And we see that the sea surface is what is changing from poleward to equatorward as it crosses the crests and troughs of the meander. On the right, we have an animation with the monthly output of the model, and we see that at the meander region, it'll be around here, there is this increased transient signal relative to the region upstream. So what are the consequences of all of this? We suggest that resolving meander patterns or fine scale in weather forecast models could increase the weather predictability downstream, because as far as I've been reading, looks like many of the weather forecasts, they take into account the sea surface temperature of the ocean 1 degree. So resolving patterns that are mesoscale resolving by the ocean could capture that 13 terawatt increase for this meander region and many others around the oceans. And the meandering of the fronts, as we saw that it deforms the mixed layer depth and enhance vertical velocity, can play an impact on biological production due to changes in nutrients and fluxes through each layer. And also has implication. It also shows implications of meanders for water mass formation, carbon sequestration, and ventilation of the ocean interior. So yeah, I'll open for a couple of questions before I move towards the second part.
Thanks, Felipe. Just virtually raise your hand, or you can start speaking if you have questions. Seb, I see a raised hand.
Hi, thanks,
Hello.
Felipe. Thank you for a very, very nice talk. Great summary of this paper. Well done. I just was curious to know a few things, but I'll stick to two. Firstly, the model, I didn't quite get it at the beginning. I need to go read the paper carefully, but you said the model was forced by JRA 55. So the model is not coupled. It's not an ocean atmosphere coupled model. So I was just wondering how you have this, how we can interpret that feedback of the ocean mesoscale back into the atmosphere for the wind stress. And well, I'll save my question if others don't have more for the other one.
Yeah, that's the thing. The axisome, it is MON6 model, MON6 ocean model, coupled to the sea ice. So it's a sea ice coupled model, forced by the JRA 55. In this case, it's not a three-way coupled model. So yeah, the definitely evaluating a product that is fully coupled by ocean, atmosphere, and sea ice could give us a final impact of how the ocean fully returns the signal to the atmosphere. At the stage with the output we had, that's what we found.
Simon.
Yeah, I guess Seb asked my question actually, but also I guess I'm thinking the composite process flashed past a bit quick, and I think how long was the model run? About
This one, 26 years for this
26 years. So of course there'll be sort of interannual and decadal variability. I just wonder how that might influence your results. Your results are brilliant. I really like the analysis, but if you split it into two periods, or you looked at different phases of the SAM or something like that, of the southern annular mode, would that influence your results? Have you tried to do any of that sort of stuff?
No, we didn't, and that's definitely a great suggestion for future work. This time series of the Meander length may give some hints
there
of
it is.
that.
Yeah, okay. All right.
Yeah. We could also explore other index to see how they match with the flexing or relaxing of the Meander. That's something we didn't explore, but there's definitely room there too.
Okay, and this was a slide I wanted to see again, so I didn't quite get. So the definition of relaxed and flexed is just based on the variability of that contour. Okay.
Yeah.
All right. And there are different ways to do that. I mean, it doesn't seem like I would guess there are, but anyway, I'll shut up for now. Karen, with the second part, please, and yeah, I'm going to check this paper out. Thank you.
Okay. I don't see any more questions. So Felipe, when you're ready, you can start the second part. Thanks.
Thanks. Okay, second part on air sea heat flux and subduction in the netting Southern Ocean. Brief introduction. This work by Langley and others in 2017, they discuss that the Southern Ocean has taken up more than 40% of the total ocean uptake of anthropogenic carbon as presented by Catwala and others in 2019. And the work by Langley, they used that classic subduction equation and decomposed the meso to large scale subduction signal using Gaussian filters, or if I think maybe 200 kilometers of decorrelation. And by this horizontal scale decomposition, they show that the mesoscale signal holds about 76% of the total subduction of anthropogenic carbon within the intermediate and mild waters in the Southern Ocean. In the recent work by Lily-Dove and others in 2022, they highlighted that the ventilation of intermediate water can be attributed to the presence of steep topography and added kinetic energy. They did so by picking the Argo floats that had apparent oxygenization values at the regions of high and not so high added kinetic energy. And they showed that the oxygen units are higher at the regions where they see concentrate eddies and standing meanders. And we also see that these patterns discussed with our recent work that indicates that meanders contribute to the subduction, and as it removes oxygenated waters from the surface to the interior, contributes to the ventilation of the ocean interior. About subduction in the Southern Ocean and the impact of the eddies, there are lots of work on that. And some examples are the work by J.B. Saleh and others in 2010. Here in the top left, you have the vertical Ackermann velocity signal, the mean layer induction signal, and also the eddy-induced subduction signal that the authors obtained by parameterizing the subduction signal from Argo products that are in a coarse resolution grid to obtain the total subduction. The authors presented that eddy-induced signal plays another one role in the Southern Ocean subduction. And recently, Lee, Matthew England, Vanna Cherovec, and many others in 2021 and 2022, emphasize that most of intermediate water formation is concentrated in the Southeast Pacific and Drake Passage by following the methods by J.B. Saleh and recent observational products that are also in a coarse resolution read perspective. And these observation approaches are effective and great for estimating the basin scale subduction, but they do not resolve the presence of fine scale eddies, as they require the parameterization using the eddy diffusivity coefficient. When you look in the literature in the North Hemisphere, there is this example by Xu and others in 2016 that they showed the relevance of estimating subduction without parameterization, as they observed that the eddy diffusivity south of the Kuroshio extension can be 10 times higher than the typical values from the Gantt-McWilliams parameterization. Moreover, the work by Madeleine, Youngs, and others in 2023 highlight a possible sampling bias by flows in their idealized model. The Lagrangian trajectories in black, they indicate that there may be undersampling by flows upstream of ridges and oversampling downstream of the ridges that could lead to a bias in coarse resolution observational products. So here we want to estimate subduction in an eddy in Southern Ocean without any parameterization using the eddy resolving model, now in a daily time series along 10 years. That is the same axis OM2 model, forced by the atmospheric reanalysis. The figure on the right shows that the same SSH contours that we used to track the polar front and subantarctic front south of Australia can also be extended over the entire Southern Ocean, as they match with the definition that fronts should lie within the peaks of the sea surface height gradient. About the methods, there is this classic subduction that I also introduced in the first part of the talk that we used it for the first paper because we were interested in the standing signal of the meander. But now, as we want to explore the eddy-induced signal, we need to use the eddy-induced subduction equation. And eddies play a significant role in the eddy-driven ventilation, as discussed in the recent review by Del Morrison and others, as these eddies can introduce an eddy-driven transport of tracers between the upper and interior ocean. And to estimate the impact of these eddies, we need to obtain the delta Z that is relative to the thickness of a density layer immediately below the mixed layer depth. To obtain this thickness, we pick the density values at the base of the mixed layer at each grid cell and snapshot of the model, and estimated the depth increment that it has at where the density increases in 0.02 units relative to the density value at the base of the mixed layer. When you have this delta Z, we can estimate the bolus velocity, the U star, from the cross correlation between the perturbations of the velocity at the base of the mixed layer and the perturbations in this delta Z, normalized by the mean thickness. By perturbations, I used a 60-degree low-pass filter in the U and delta Z time series. That's what I mean by perturbation here. And we can also obtain the vertical bolus velocity from the continuity of the horizontal, from the continuity of the horizontal bolus velocities. Then we can follow David Marshall, 1997, to estimate subduction using both the Eulerian or mean and eddy-induced terms. So now we have 4 terms for subduction instead of 2. Okay, let's see what we got. First, I'm showing this delta Z term, the thickness of this density layer below the MLD. And on the left, the timing, on the right, the standard deviation. And at the moment, we are not aware of other works to compare our values. So if anyone knows, please share it to us. What gives us confidence of the results we found to use them to estimate subduction is that the delta Z values are high. South of Australia, south of the Campbell Plateau, the Southeast Pacific, south of the Weddell Gyre. And these are the regions that we know that mold water, intermediate water, and bottom water form it. So it's fine to expect this increase in the thickness of the layer below this isopycnal layer below the MLD. Okay, and then exploring the subduction variables, we have the mean layer reduction on the left and the eddy-induced layer reduction on the right. using that delta Z term and the perturbations of the velocity and the MLD gradient. We see that the mean layer induction shows the highest subduction signals at the subantarctic front region and the polar front zone. And the air-induced term is not as high as the mean term as we see comparing A and B. Turning to the vertical velocities, we see the large-scale signal of upwelling around near Antarctica and downwelling south of the ACC, downwelling north of the ACC. And we see that the vertical velocities are higher at the regions where the ACC meanders and sheds eddies. In terms of the vertical bolus velocity, we see that increases in magnitude mainly at the topographic features, Southwestern Ridge, Kerguelen Plateau, and many of the others. We wanted to estimate the net impact of these subduction values for mold water and intermediate water subduction. To do so, we integrated then between isopycnals for mold water and intermediate water. Mold water isopycnals we chose were based on the distribution of the potential vorticity minimum. Mold water is comprised the regions of low potential vorticity values. And the isopycnals for the intermediate water, we used those that we found for the region south of Australia, in the TS diagram that I showed previously. The 26.9 and 27.9 could bound that layer, and evaluating that for the whole Southern Ocean perspective, we see that these isopycnals also capture the salinity tongue of low salinity in the Southeast Pacific as reported by the observations. Then we integrated each of those subduction variables between the mold water isopycnal for this figure we have here. In solid, we have the integral for the mean lateral induction term. You see changes from abduction to subduction all around the Southern Ocean. Vertical velocities, as they are downwelling, they will lead to a case of subduction. That's why we see positive here, but it's not as high as the subduction induced by the layer induction, mainly at the region south of Australia. And the interesting result we see here is the comparison of the air-induced layer induction and the vertical bolus velocity by the dotted and the dashed line, because we are seeing that they are anti-correlated. There is a residual between them, but in this study, as we are estimating each of these terms individually instead of parameterizing, we can see that they nearly cancel each other. And the previous works that parameterize it using observations, they only got one single term as they induced it, and they couldn't see this canceling between these terms. They do not cancel out. There is a small residual between them, but they are anti-correlated. We also, and then we got the sum of all of these four individual terms, integrated then for the mold water isopycnal layer to obtain the total mold water subduction. And we also compared with the bathymetry contour nearly around the mold water region, and we see the relevance of bathymetry in shaping the subduction and abduction regions for mold water. We did the same for the intermediate water isopycnal boundaries. Again, we see the dominance of the mean layer induction in the subduction patterns. Here, as mold water is at a region of upwelling, the vertical velocities in dotted lines will cause abduction instead of subduction. And again, the air-induced layer induction and that vertical bolus velocity are anti-correlated. And in this work, we saw that the residual between them leads to abduction instead of the subduction suggested by the parameterized studies. For the total intermediate water subduction, again comparing to the distribution of bathymetry, see that there is about one is variable, being subducted south of Australia at the Macquarie Meander region, about 1.5 at the Pacific Antarctic Ridge, that there is another meander, and about 5 is variables at the Drake Passage. as there are meanders at these other locations, I think it's fine to speculate that the meander-induced subduction mechanism we saw off Australia can also be occurring at these other locations. One question that we can arise from this plot is that why we don't see much, or let's say maybe not at all, subduction at the Atlantic sector. To give a suggestion for an answer, I would like to talk about the air-sea heat flux patterns first. And talking about then, we have, let's say, sensible heat flux, latent heat flux as the turbulent. And we see that the Atlantic and the Indian sectors, there's the heat exchange around the ACC fronts is nearly new. But when we go towards the Pacific sector, we see heat loss by the ocean around the polar front and subantarctic front. Well, the polar front in the Atlantic and Indian Ocean is at around 50 degrees south, but in the Pacific, it is at 60. So as I also saw in the talk by Simon Josie, we are aware that the poleward displacement of the polar front leads to poleward displacement of warm water to a region of polar atmosphere, and there will be heat loss by the ocean at this location. That we don't see much of that happening in the other sectors. And as the ocean loses heat to the atmosphere through sensible heat flux, it increases the ability of the atmosphere to hold more vapor, and as it's gaining heat from the ocean. Then it increases the humidity gradient of the atmosphere relative to the ocean at the Pacific, further increasing the latent heat flux that is intensified at the Pacific, and we don't see much of that in the Atlantic and Indian around the ACC fronts. For the other terms, they are mainly related to the latitude, so yeah, they won't explore that much long wave and short wave radiation. And why I brought all of this to suggest and bring this discussion that the air-sea heat flux asymmetry discussed by some Josie, Veronica Tamzit, and many others. And as we see in the net surface net heat flux signal of surface heat loss in the Pacific and heat gain in the Atlantic, can lead to a high mixed layer depth gradient at the Drake passage that impacts dominant subduction term, that is this lateral gradient. We are aware that winds are relevant for the distribution of the mixed layer depth. But as we saw for the Macquarie meander, as we can also see here at the Campbell Plateau meander, the regions of intensified heat gain leads to shallower mixed layer depth, and regions of intensified heat loss leads to deeper mixed layer depth. And we see again that for the ACC pathway nearly around the fronts, this intensified heat loss in the Pacific leads to this intensified deeper MLD at this location. And the change from heat loss to heat gain at the transition from Pacific to Atlantic leads to a gradient in the mixed layer depth at that location that influence the dominant subduction term. To explore this in more detail, we also integrated the surface net heat flux for the mold water isopycnals and compare that, and that's the red line in this figure. And we compared to the subduction, the integrated subduction for the same isopycnal boundary. And for a large scale perspective, you can see that the changes from heat gain to heat loss influence the changes from subduction to abduction distribution around the Southern Ocean. In a large scale perspective, there are some mesoscale effects in certain regions. The large scale pattern becomes even clearer when we do the same for the intermediate water boundaries. Well, in the Atlantic, we have the heat gain, the increase of the heat gain as it moves towards the Indian sector. And then when we reach the Pacific sector, there is this heat loss by the ocean within the intermediate isopycnal boundaries that we can see in black in the figure in the top right. And when we compare that to the integrated subduction patterns, we see that it follows the changes from where it changes from heat loss to heat gain, it changes from abduction to subduction. And it's the region where it increases the most is at the Drake passage. Okay, what is the relevance of all of this? With this detailed and careful analysis of the subduction values, we can point subduction hotspots for mold water and intermediate water formation all around the Southern Ocean, that it's relevant for the regions where nutrients are subducted, gases and heat, before they are spread all over the other ocean basins. So we saw energetic regions lead to water mass formation as the locations of steep topography increase the intermediate water ventilation, as well as the subduction of mold, both mold and intermediate waters contribute to that. These discussions are relevant for both the Southern Ocean overturning south and the global overturning circulation. And it has consequences for the description of the pathways of the global overturning circulation and regions of removal of carbon from the atmosphere. And it's pivotal to describe interactions between decadal to mylenal impacts on Earth's climate. Finally, we highlight that the large asymmetry of air-sea heat flux has a direct consequence for the subduction of mold and intermediate waters, as the ACC fronts encounter bathymetry obstacles along its pathway. It deviates poleward at the Pacific, leading to different sensible and heat flux exchange that has potential consequence for the distribution of subduction in the Southern Ocean. And that's it.
Great, thank you, congrats. That's really nice, Felipe. Thanks very much. I will open to any questions. Again, just raise your hand or unmute yourself. If you you can add to the chat as well. I'm monitoring the chat, so if you want to have any questions, you can throw it there too. Any questions? I can start. Give people time to think. Can you explain to me a little bit about the bolus velocity? Just wanted to try and understand that a little bit more.
All right. Okay, here we are.
Thanks.
Do you want to talk about its method or the philosophy and impact behind?
Yeah, well, I just wanted to understand a little bit better and how it was used. That just went over me a little bit, that's all.
Oh, okay. Yeah, to obtain that, we found the density value at the base of the pixel layer depth at each snapshot. And then we estimated the depth increment where it increased in 0.02 units. So we evaluated that just in a small layer right below the mixed layer depth, where this change in the thickness of the isopycnos can introduce changes in tracers from the isopycnos.
I got you. Okay, well, that's really nice. I mean, that leads to my second thought, which was you using the model, which is a 0.1 degree model. And of course, your linking is that the air-sea heat fluxes are the dominant drivers of the mixed layer variability, and this ultimately controls the subduction. Is that a fair way to think about it?
Could you say it again, please?
My understanding was that your in your summary, it's the heat fluxes and the sort of asymmetry between the heat fluxes that controls the mixed layer depth, this bolus velocity, and therefore the subduction. Is that a fair way to think about it?
Oh, it's definitely part of the conclusion.
Because and in the area of Kerguelen, you don't find any subduction, and you say, well, the surface fluxes there are primarily positive, so you have mixed layers that are not sufficient. My one thinking there was of Leah Siegelman's work using the seal tag data and looking at the role of smaller scale processes that act below the mixed layer depth that are important for vertical distribution of heat. Could you say anything about what potential implications that might have? Because obviously with the model, you don't directly resolve those mechanisms.
I will give some comments about that, but first, I'll also talk about the first question. That what point is that, yeah, the contribution of the vertical bolus term. The vertical bolus leads to, you see it here, yeah, it leads to abduction, but as it is anti-correlated to the add-induced layer induction, it nearly vanishes the add-induced signal, suggesting that the mean layer induction is the dominant term for the system. And the studies that had the add-induced subduction as a single variable, and we get like here, they didn't have these two terms individually. They parameterized it then as a single one. In our case, we are saying that yes, they contribute to subduction. However, they nearly cancel out each other. It's relevant to estimate them because there is a residual, but they're not as relevant as the mean layer induction.
Right.
In terms of resolution, let me see if I have an extra figure to talk about that. I don't have the extra figure. In any case, in terms of the resolution, the model is 10th degree because at the equator, it has 10th degree resolution, but the resolution increases towards Antarctica. As far as I remember, I think the resolution at the Antarctic basin will be 3 kilometers, 4 kilometers or so. At the Meander region, it is 7, 8 kilometers. And yeah, it does not fully resolve the submesoscale dynamics, but all the mesoscale signal were resolved by the model.
Okay. Great, thanks. Do we have any other questions? Seb?
Hi again. Thanks, Felipe. Well, I don't deny there's obviously this connection between the air-sea heat flux and the subduction regions of the Southern Ocean. What I didn't really get was the contribution of salinity, which seems to be, is known, I mean, now quite fairly well in the literature. And I think Alberto has some recent work about the role of salinity in these deep mixed layers versus the heat flux. So how can you maybe, reconcile both of those contributors to these patterns you see on your maps in the model?
Yeah, the freshwater fluxes, the contribution from salinity is definitely another factor to contribute for the total buoyancy forcing, in addition to the air-sea flux. But you can also think in terms of the work by Almeida, Matthew Maslow, and what was his supervisor for Mauricio Mata, 2021, that they say that the air-sea heat flux is more relevant than the freshwater fluxes. And there's another work that I cited there, I forgot the name now, that they bring this relevance of the air-sea heat flux relative to the freshwater, at least for the open Southern Ocean. And we are not close to the Antarctic margins. And another reason for why we chose to mainly evaluate the heat flux instead of salinity was because of this link between the heat flux distribution and the mixed layer depth. And the mixed layer depth is one of the terms for the dominant subduction term. But definitely, further work can be done in terms of exploring the overall buoyancy forcing by combining both heat flux and salinity fluxes. for the final subduction result. In any case, it is sufficient at first order to explore this in terms of surface 90 flux. That would be what I would say.
Great. Okay, I have one final question from my side is did you compare these to the results of Lily Dove from the observed subduction regions? I guess that could give some added, I guess, validity to, or comparison at least.
Yeah, I didn't make this comparison, but it definitely can be done. In her work, it was mainly about ventilation. It is part of the subduction discussion. But yeah, I could definitely think of seeing the regions where the model shows high eddy kinetic energy and seeing high and not too high eddy kinetic energy and see how subduction increases or not at these locations. Yeah, definitely a great idea of following.
Okay. Thanks. Any other questions? I don't see any hands. Well then, just to say thank you very much. I really appreciate the effort to share your work, and yeah, thank you again, Felipe, and have a good rest of your day. And thanks
very
everyone
much
for joining.
the space, Marcel, in organizing this. Really appreciate it.
Sure. Thanks.